All right, today we're cracking a code that has, believe it or not, stumped humanity for centuries. We're going to see how some seriously cutting-edge AI is taking on one of the oldest puzzles in pure mathematics. And this is a story that stretches all the way from ancient Greece right into the future.
So it all revolves around this question that honestly seems super simple on the surface. I mean, think about stacking oranges at the grocery store. It feels like a child's game, right? But this simple idea has resisted some of the greatest mathematical minds for hundreds and hundreds of years. And that is the hook for today. We're going to explore how a totally new kind of AI didn't just make a little bit of progress on this ancient puzzle. No, it smashed records and discovered mathematical structures that, get this, humans had never seen before.
Okay, so what exactly is this puzzle that's caused so much trouble for so long? Let's break down the fundamentals of what's called the sphere packing problem.
So at its core, sphere packing is really all about efficiency. How can you cram the most identical spheres into a given space without them overlapping? Now, you can probably picture this in 2 or 3 dimensions, right? Like circles on a page or those oranges we talked about. But what about 4 dimensions, or 8, or 16? Suddenly, our intuition just completely breaks down, and the number of possible ways to arrange them explodes into infinity. That's where things get, well, really complex.
And what's really striking here is the timescale. I mean, this is not a new problem. It has roots in ancient Greece. And just look at the jumps in progress. It took until 1942 to solve it for simple flat circles, then all the way to 2017 to finally, formally prove the 3D case. The 8-dimension solution in 2022 was so incredible it actually earned a Fields Medal. That's like the Nobel Prize for math. And now, just a few years later, an AI comes along and pushes the boundary in 12 different dimensions at once. It's like the slow, centuries-long crawl of progress just suddenly hit warp speed.
So you might be asking, why is this so ridiculously hard? I mean, can't we just throw a supercomputer at it and brute force the answer? Well, it turns out sphere packing is a unique kind of nightmare, especially for AI. And this slide really gets to the heart of the problem. You see, AIs like AlphaGo are amazing at problems that are hard to solve, but really fast to check. You know instantly if a move in Go is legal, right? Or if a protein fold is valid. But with sphere packing, just checking if a single proposed arrangement is any good can take a computer days of number crunching. This slow-to-check thing makes all the usual trial-and-error AI methods, well, they're just completely impractical.
Okay, so this bottleneck is where the really heavy-duty math comes in. The best technique humans have is called the 3-point method, and what it does is pretty clever. It turns this geometry puzzle into a giant optimization problem. You can kind of think of it like a massive multidimensional Sudoku puzzle, which mathematicians call a semi-definite program, or SDP. The trick is, to find the best possible version of this puzzle, you have to search through this ridiculously huge space of different rules and starting numbers. And here's the killer part. Solving just one of these SDPs is incredibly slow, so you just can't try millions of them. It's not an option.
So how on earth did the researchers get around this massive bottleneck? Well, they developed a completely new and much, much smarter strategy for the AI.
Instead of just guessing or trying random things, they reframed the whole thing as a game. The AI's job is to play this SDP game and strategically build the best possible version of that math puzzle. So it's not about trying everything, it's about making smart, one after the other decisions to win. And here's its game plan, broken down into a 4-step loop. First, it makes an educated guess. It proposes some parameters for the problem. Second, it constructs the sort of vocabulary of valid mathematical puzzle pieces it can use. Third, and this is cool, it uses a strategy kind of like the AI that mastered Go to intelligently assemble those pieces into what looks like a promising solution. And finally, it actually solves the puzzle, learns from what happened, and then uses that new knowledge to start the loop all over again, getting just a little bit smarter each and every time.
And this brings us to the really key idea that makes all of this work. It's called sample efficiency. This is not a brute force AI that just tries a billion things. It's a strategic AI. It's designed from the ground up to squeeze every last drop of learning out of every single super expensive calculation. Every move it makes in this game is like a smart, informed bet that's designed to get it closer to the answer with the absolute minimum number of tries. Okay, so all this clever strategy, did it actually work? Well, let's get to the payoff and take a look at the groundbreaking results.
Oh, it worked. It worked spectacularly. The AI set new state-of-the-art upper bounds, which are basically new world records for sphere packing in 12 different dimensions. And we're not talking about tiny, microscopic improvements here. I mean, if you look at this table, you can see the new AI-based bounds are just significantly better than anything we had before. In dimensions 4, 5, 6, 10, and 16, it just systematically pushed the frontiers of what we know. But this is where it gets truly fascinating, for me anyway. The AI didn't just find slightly better numbers using the old methods. No, it discovered fundamentally new math. Think of the solution being built from like mathematical Lego bricks. Well, this chart shows that over 80% of the bricks the AI chose to use were completely new, types of polynomials no human had ever used for this problem before. It was literally exploring uncharted mathematical territory. And even within that discovery, a really clear pattern emerged. The AI learned that the most powerful building blocks, the most useful Lego bricks, were these polynomials of low degree. Basically, the simpler pieces. These are the components that give the whole problem the most flexibility. It figured out, completely on its own, which parts of the puzzle gave it the most bang for its buck, and it just focused its attention there. Okay, now for the ultimate test. What happens when you point this incredibly smart AI at a problem where we actually already know the perfect answer? So, the researchers turned their attention to dimension 8. Now, as we mentioned earlier, this case was famously solved by the brilliant mathematician Marina Vyazovska. So they gave the AI 0 clues, absolutely no hints about this known magic solution. The big question was, could the AI's own strategic search, guided only by the pure geometry of the problem, start to independently figure out the properties of that perfect answer all by itself? And the result was just astonishing. The AI started to discover functions that looked more and more like the special function Vyazovska had discovered. It began to replicate the key mathematical signatures of the perfect solution. Not because it was told to, but because it discovered that this was simply the most optimal path through the entire problem space. It found the right path on its own. The research paper puts it perfectly, if a bit academically. They say it can autonomously approximate deep analytic features. What does that mean in plain English? It means it found profound mathematical truths just by exploring the shape of the problem. It figured out the answer without ever seeing the answer key. All right, so let's zoom out for a second. Why does any of this matter beyond just a really old, kind of abstract math problem? I mean, what does this actually mean for the future of scientific discovery? Because this isn't really just about stacking spheres. This is a blueprint, a new paradigm for a completely different kind of AI, a sample-efficient AI that's tailor-made for problems where every single experiment is incredibly slow or expensive or both. Think about a particle accelerator run, a new drug trial, or a materials science experiment. It's a tool for problems that are governed by hard, unbreakable mathematical rules, not just fuzzy statistical patterns. And that leaves us with a really tantalizing question. For centuries, scientific discovery has been limited by the speed of human intuition. But if an AI can now discover fundamentally new mathematics all on its own, what other impossible problems in science, in medicine, in engineering could this new kind of AI tackle? Are we on the verge of an era where the most profound breakthroughs are no longer just made by us, but maybe they're made for us?